Swayam Prabha. Digital India. Educated India.
Okay, good morning. Good morning. So let us complete the topic that we have started yesterday, which was the distribution of lateral forces in the lateral load resisting elements. We have, set yesterday a methodology which allows us, once we know the wind force, the earthquake loading, or the horizontal force, which is due to vertical tolerance, we have devised a methodology to distribute, to understand how this load, which is the load applied to the building, is shared among the different elements of the lateral load resisting systems. But there is also the need, you see, for example, these are shear walls, okay? And you see here, this is basically, solid, but there is an opening here. This is solid, but here you have, even if they are small, you have openings. Sometimes, as we have said, the lateral load resisting system also incorporates staircase cores. And especially if you are in an apartment building, on the staircase, on the landings, intermediate lengths, you will have some windows. Also, in that same core, you have the entrance doors to the apartments which have to be allowed. So you have openings. And what does this imply? Well, this is a very simple sketch. Even if it seems theory, this is a design application, okay? So imagine that you have a shear wall which is solid, monolithic, with no openings. And you have a typical lateral load distribution, which generally is linear with the height of the building start from the ground floor. Well, this applies, for example, to earthquake. This applies in some cases also to wind. Wind loading is constant up to a certain height, which, depending on the topography situation, can go from a few meters to about 10, 15 meters. But then up to about 200 meters height, well, it increases logarithmically according to most of the codes, but you can also linearize it, especially if you do not have very high-rise buildings, you can use a linear distribution. Well, first of all, the design of a shear wall, it's a matter of strength, but it's also a matter of stiffness. And the higher you go with the building, the more the design problem will become a matter of stiffness and not of strength. Because, we consider, for example, 1% of the height of the building as a limit, okay? If you are on a 1%, oh, sorry, it's not 1%, 1 per mil, 1 per mil. If you are on a 60-meter building, 60 meter is a medium height building. Okay, what is 1 per mil, 0.1% of 60 meters? It's 6 centimeters. So you will still start feeling this. But if you go for a very high rise building, 200 meters, 300 meters, 400 meters, it means 40, 30 centimeters, one way and the other way. So this brings into place two considerations. First of all, you must design all the elements of your buildings, including connections, so that they allow this movement. But the other thing, what about the comfort of the people inside, where you feel moving, a building like this. I just go back one slide because I have a little space to write. In Milano, one of the most iconic buildings that we have is the so-called, no, let's draw it this here. It's the so-called Pirelli skyscraper. Okay, the Pirelli skyscraper has a shape like this. And this was this direction, this is more or less south-north, which is according to the main winds. Okay, main winds come from the north. And as a matter of fact, our airports also have orientation south-north, and you always land from the south because you always land with that breaks you. Okay. This was designed originally to host the offices of a very big company, and at the uppermost 2 floors, they were the apartments and the very, very big reception hall of the family owning the company. Okay. The concept was by Pierluigi Nervi, very famous architect and engineer. He was the father of ferrocement. Well, not more than 10 years after the construction of the building, the family abandoned it. The issue was the vibration in this direction. Because you see, this building is very stiff in one direction, which is the direction of the main winds, but it's, not much stiff in the other direction. The building is safe. It even survived in early 2000, the crash of a one-person airplane, like a Cessna or something like that, which crashed into its top floor. Okay, it even survived that. So the building is structurally sound. But the comfort of the people was, disrupted by the fact that the stiffness was not adequately considered. So if we have a solid wall like this on the left, the stiffness is proportional to this dimension, to the cube of this dimension. And the mechanism of resistance, you can imagine that at the bottom of this, you can imagine that here at the bottom, you have a bending moment. Well, you have the self-weight of the building, and you have a bending moment and the shear force, okay? And the bending moment, in principle, will give you a distribution of stresses like this. Tensile on one side and compressive on the other. But this is elastic. This is elastic. When you go for a strength problem, we know that in concrete, in reinforced concrete mechanics, we go for nonlinear behavior of the material. So you can expect that there will be some compressed concrete here, and you will have the tensile force here due to the steel. As a matter of fact, if you look in the codes, the design recommendations for this kind of walls is that you identify here a region equal to 0.2 h. Small h is the width of the cross section. So identify 2 regions, 20% of the depth on one side, 20% of depth on the other side. And you consider that the wall resists with a mechanism of compressive and tensile forces in those 2 regions. So it's there where you concentrate the resistance of that wall. So you resist, as it's written here, with a couple of forces, tensile and compression, which have an inner lever arm of 0.08 as it's written there. And you can easily imagine where that 0.08 comes from the assumption that we have made. As a matter of fact, if you look at typical reinforcement detailing for these kind of walls, you see that this is the cross section, and you have the reinforcement likely concentrated here and here. I'm drawing, examples. And here you will have some stirrups as well, or probably even something like this, always closed stirrups. Well, it's not that in the other part of the wall you do not have reinforcement. You will also have some reinforcement here, but will be less dense, more loosely spaced. But the important thing is that to resist this action, you have the wall width of the wall cross section, because there is no opening. So the flow of stresses is continuous. What if you put openings for windows, for doors, something? Well, actually, if you put openings, you are dividing your wall into two shafts. And if you have a door, which is generally the minimum opening of a door that you have. Well, consider that this is not a door inside an apartment. That doors are 90 centimeters typically. This is a door, main door for offices or for a apartment building, the entrance door. How wide is that? Do you have an idea? Yeah. For example, in hospitals you have wider, but at minimum is 1.2 meters. 1.2 meters is considered that two people. Consider that this with us, the breadth of our shoulders is 60 centimeters. Two people can pass through. So minimum is 1.2 meters. Even more, because in hospitals you have to pass through with that and so on. Or if you have an office, you have to consider that also something. So if shear wall is typically, let's say, 4 meters wide, and you cut it off 1.5 meters, even 1.2, 4 meter minus 1.2 is 2.8. Divided by 2 is 1.4. So actually, with these numbers, this is 1.4 over 4. 1.4 over 4 is 35%. 35%. So the stiffness of each of these shafts is 35% to the cube, the one of the solid wall. Try to calculate how much is 0.35 to the cube. 0.09, 0.043. So it's just 4%. So you see how much have we lost? Well, then you have to multiply by 2, and it's 8%. So we are an order of magnitude less. What does it mean? What does it mean? Well, on one end, the building can be more flexible. So when you go for earthquake, it can mean that you dampen a little bit the forces. But for wind forces up to a certain age do not depend on the stiffness of the building. So the wind force are those. So you have the same force, but your stiffness is 10 times lower. So you can expect deflections which are 10 times higher. So it becomes much more demanding to guarantee the deformation limit, the serviceability limit state. But, and also with respect to the strength, as you see, now you have two shafts, and their inner lever arm is not the wall width of the wall. It's 35% of it. and you have to resist half of the force at least if you want to share and to split it. So you also have a penalty because you have to resist a force which is half, but you have a lever arm which is 35%. So you have a magnification factor of about 1.6, 1.7. So it's a problem of, needing to design with reduced capacity. But there is another issue. We must ensure that these two walls, they behave together. Otherwise, they are independent shafts and they do whatever they want. So we must guarantee that there is a flow of forces which goes from here to here. These coupling or connecting beams must guarantee the fact that even with the openings, the two shafts work together. So the design of the coupling beam is a very demanding task in shear walls in general and in precast shear walls in particular. And what does this imply if you have to guarantee this? Well, in the codes, especially for earthquake design, you find that you have to provide diagonal reinforcement. Well, why diagonal reinforcement? Because as a matter of fact, the force which has to pass from one side to the other is like a shear force like that. It's mainly a shear force. But that shear force, the earthquake does not come only from one side. The earthquake goes here and there. The wind is the same. So it can be like this, but it can also be like this. Exactly like that. Well, what if we put, it's possible, what if we put, we will see, if we put longitudinal reinforcement? How a bar resists that force? Well, a bar resists that force basically, well, not merely to shear in the cross section. The cross section is small. It resists through dowel action. And dowel action means that the bar is pushing against the concrete. So at a certain point, you have cracking and crushing. If you have diagonal reinforcement like this, you see this force here will be taken through an action which is tensile for the bar, which is the most natural way for the bar to work. But as we can see from this figure, the requirement for this kind of reinforcement can be so high that you have a very high congestion because, you see here, you have a bundle of diagonal reinforcement because you have to put on either side of the wall. A wall is 20 centimeters thick, so you have to put on both faces. And you have, well, here it's not much clear, but you also have to, connect to, tie this diagonal reinforcement with stirrups. The other main thing, you see the opening is here, and the other opening is here. So this, you can imagine, is the coupling beam from the top of the door up to the floor of the upper floor. And they have to work at this edge cross section. But it means that from that edge cross section onward, they must be bonded into concrete. So you need, from that point onward, to calculate the development length. So actually, I think I have some other pictures here. Well, you see here. You see the bond length, the development length, extend well upward into the top floor wall and downward into the bottom floor wall. Yeah, they are using very large size bars in this case. Yeah. And you also see these two shafts, how heavily reinforced they are. You see there is one main stirrup here, but you can see also hooks in between because you have to connect all the reinforcements. So the design of this kind of details is actually very demanding. For example, there is a whole, very, very big, very solid research and application program in the US to use prefabricated coupling beams, which are made with fiber reinforced concrete, high performance fiber reinforced concrete, or ultra high performance fiber reinforced concrete. So you come with these elements. They have just a minimum longitudinal, in most of the cases, longitudinal reinforcement that can allow you to connect. You mount them, and then you complete the casting. But now let's develop a very simple, case study example on how do we design a coupling beam for this wall. So let us imagine that we have this wall with a cross-section depth equal to small h, and there are some openings in the middle, symmetric, so that you divide the wall into two shafts, h1 and h2, which are equal. The symmetry of the opening is also quite important, because on that, it depends on how your coupling beam behaves. Because if you have a coupling beam which frames into two walls of equal stiffness, you can consider that the coupling beam behaves like this, like a beam clamped at both edges. And when you assign it the deformation that the wall undergoes, it's a side deformation. So you can imagine that this, two edges, they rotate. So you have a deformation like this with the counterflexure point in the center. This is a balanced situation, allows you for a better layout of the reinforcement. If for any kind of reason, which can be simply the layout of your apartment's doors and so on, you have one of the two walls that it's much narrower, much shorter than the other. So what you will have, for example, if H1 is much smaller than H2, the scheme that you must use is this one. And so when you have the rotation here, what you will undergo is a deformation like this. So this is also, a very simple approach through which you can use your solid mechanics basic concepts to design this. Because, the design is not, having a handbook of formulas that you apply. It's being able to simplify, or better, not to simplify, to model the reality, the physics of the problem with some tools that we are able to handle. And in precast, we will see with the design of the connection, in precast, when you go to the connections, the ingenuity of the precasters has developed a huge variety of connections. So you will not find a handbook, a textbook, which tells you this connection design in this way. No, forget it. It's not the purpose of any university course to give you a handbook of formulas. The purpose is to give you, how does this connection behave? Which are the mechanisms? Tension in the bar, bond, dowel action, compression in concrete. So which are the models, the physics models and the mathematical models which describe these behaviors? Apply them and design your connections. You may invent your connections. You work in companies. You can patent your connection. You are doing research. So you will not find that connection in the handbooks. Forget it. You have to learn how to design a connection, which does not mean a formula, means the mathematical principles. Okay? So then a very simple model. How do we need to calculate these forces here? You know, the force that the coupling beam must transmit from one another. So let's single out a modulus of the wall, which is an interstory one. So you have the coupling beam at the center, half of the opening on the top, half of the opening on the bottom. And the interstory depth is capital AI. Well, in a building, it's always like that, except for the lower half of the bottom floor and from the top half of the bottom floor. We know we can calculate, because we have this distribution of shear forces. We can calculate which is the total force which pertains to that floor. So we will have the, I don't know, well, probably it's very clear. Okay. You will have an interstory shear force here and an interstory shear force here. So these two interstory shear force, VI, they give you a moment which is VI times the height of the building, the interstory height. And these two forces, which are the forces in the two shafts, they must equilibrate this moment. How do they do? Through the inner lever arm Z. So if your coupling beam must restore the continuity between the two shafts of the walls, it has to be likely if the opening does not exist. So this is the same mechanism that we have seen for the solid wall. And so these forces which have to pass from one side to the other are exactly equal to this. So this force here has to pick up this force, transfer here, and bring back. So you have to design your coupling beam for a force Q, which is equal to the shear at that story times the interstory height divided by the inner lever arm of the wall Z, which is 0.8 of the wall cross-section depth. Well, you can imagine how demanding is this building, because you know this is actually a cantilever. Okay, and here on the top the shear force is 0. As long as you go down, you add portions of that. So the more you go down with your coupling beams, the higher will be this. So actually your design requisites will become more and more demanding as long as you go down, or as long as you go higher with the building and you design the lower cross section. We have to cancel something here. So we use a geometric scheme. Okay, so this is our, let's enforce this with some colors, which is better. So actually, this is my coupling beam. And you see the force Q there, is put at a generic position. This is the centroid of the coupling beam, is put at a generic position E. where how do you estimate that E? Well, that E, it depends on where your counterflexure point is. Because the counterflexure point is, you know, in a beam where your moment is 0. So if you cut your beam there only shear forces pass. So actually, as we said, if our layout of our openings in the wall is reasonably symmetric, the counterflexure point will be in the middle of the coupling beam. So that E will be 0. If the wall, the layout of the openings is strongly non-symmetric, well, the counterflexure point is at the edges, and so that E will be half the length of the coupling beam. Now, you see, we have highlighted a little bit this, you know, position here. You see, we have these 4 points. This here. And you see, they are put at 0.08 times the depth of the coupling beam inside the wall and, you know, upside. Why this? Well, let's try to make a step back. So we have said, okay, imagine that this is a door in an apartment building, the entrance door, 1.2 meter wide. The interstory 8, how much is that? Well, in Europe, the minimum is 2.7 meters. Don't know how much is it here. Huh? About 3 meters. Okay, 3 meters. In Europe, it's minimum 2.7 meter. If you are in high mountain regions, you can go down to 2.4 because that the volume becomes smaller, and for heating or cooling now, it's more efficient, you know, because you have a lower volume of air to heat or to cool. But okay, we have a, let's say, 3 meter depth, and the customary 8 of a door, how much is that? About 2 meters. Okay, so 3 meters minus 2 is 1 meter. So this coupling beam is 1 meter deep and 1.5 meter long. Can we call it a beam in the structural mechanics, conventional structural mechanic assumption? No. What kind of, if you go back to the lecture that we made on Friday, what kind of element is this? Is a D region as a wall. So we have to, you know, design. Now imagine that we have a reinforced concrete cross section, BH, and we have our reinforcement here. This is AS, and this we call D. D is the effective depth. Well, we can say that H is equal to 1.05 1.10 d, more or less. Okay. If we have a bending moment, we know that we have a distribution of strains like this, linear, and this is the neutral axis depth x, and epsilon cu is the ultimate strain in concrete, which we have said can be 0.0035. Okay, and to design, we associate to this strain diagram, a distribution of stresses which is made like this. And you have compressed forces in concrete applied over a depth which is 0.8 x. And you have the forces in steel, and we assume that the steel is yielded. Okay? Now, in all the codes nowadays, since you know the steel is a very ductile material and its rupture strain is 6, 7, even more %, in the codes we consider that steel is an infinitely deformable material. So there is no strain limit to steel. But in some older design codes, there was also a strain limit to steel. It was stated that, you know, it's better if this strain here remains below 1%. And why this? Well, because one of the assumptions that we make in reinforced concrete design is that there is perfect bond between steel and concrete. So the concrete around that bar, even if it's in tension and we neglect in the design, you see there is no tensile stress in the concrete part. But the concrete is there and has to follow the steel. Otherwise, you do not guarantee this concrete part here, even if it does not participate in the strength, it has to guarantee the connection. Otherwise, you have bars which go by themselves and you have concrete which goes by itself. So pretending or demanding that concrete deforms up to 1%, it's a very, very huge demand. At that stage, the concrete is very, very cracked. So the reason for which there was this fictitious limit on steel was because, you know, the surrounding concrete at that deformation limit would have been no longer able to guarantee the bond and the continuity. But so if we set epsilon cu equal to 0.035 and epsilon s equal to 0.01, this and this, how much is x in that situation? Can you calculate it? Do it. When epsilon cu is 0.0035 and epsilon s is equal to 0.01, how much is x? 0. When I was a student, we learned at 0.2593D. Yeah. But you know, this huge precision of digits for us civil engineers, it's a little bit meaningless. We can say 0.25 or 0.26. In both cases, it's the correct answer. It's 0.25 or 0.26 D. And we use, in order to calculate it, the similitude of triangles. we say that 0.0035 divided by x is equal to 0.01 divided by d minus x. So we write, and you find that x is equal to 0. I just go quickly because you have already done it, which is close to 0.25d. Okay? So if x is 0.25d, how much is this? Point 2d. Okay, 0.2d. And since d related to h is h divided by 1.05, 1.2, even a little more if your beam is squat, you know, we can say that this depth is around 0.16, 0.18 h. Keep this number, okay? Because now we go back here. If you hypothesize a distribution of compressive forces over about 0.16 h, which is what we have said, because this beam is very deep, so the proportion between d and h are not like for band element. Where is the centroid of this distribution? Is at 0.0 h. So you see, this methodology is not written in a code. This methodology is not written in a code. It's not written in a guideline. It's something that somebody, we proposed to design. But what is it based on? It's based on all the background that we have on reinforced concrete mechanics. Well, and then, okay, we understand why we have to go up of this, but why we have to go inside? Well, because the flow of the stresses actually will be inclined like this. And so you can imagine that you go also your strut, because we will use a strut and tie model, your strut will not be anchored, your strut cannot be anchored at this corner point, but must be anchored into some kind of solid concrete region. But you see, these assumptions here, these are geometrical assumptions which are based on the concrete mechanics. These assumptions here are even more important than the formula that we are going to use to calculate the forces. We will employ a strut and tie mechanism, as a matter of fact. And as we have said Friday, we are hypothesizing that the element behaves in such a way. But then the way in which we design it and the way in which we detail it will be responsible for the element to behave exactly like that. So one mechanism that we can employ is this one. We hypothesize diagonal ties, and the diagonal tie, which is this one, you have a force which is equal to Q, the vertical force, and you have to calculate the diagonal force. Well, there is this parameter lambda. Which is equal actually to L, and L is equal to the opening the 1.2 meters or whatever it is, plus 0.0h plus 0.0h. Divided by z, and z is the depth, minus 0.08 minus 0.08. So this is the geometrical slenderness of the coupling beam that we use. Now, this formula here, no need to memorize it. No need to memorize it. This comes from an equilibrium and from trigonometry. Very simple. So you have a vertical force Q, which is the one that we have to calculate. This is a vertical. So you have, this is the force in the steel. The vertical projection of this force must be equal to the force Q. So the vertical projection is this times the sinus of this angle, and you correlate to the slenderness of the beam. But there is another assumption. We have two bars, one diagonal going upward, the other one going downward. If we have a vertical force pointing upward, this diagonal is in tension, and this diagonal is in compression. And you can say, well, but by both diagonals will contribute to the force. This equation here, which is simply a force equilibrium, states that only the force, the vertical component of the force in the tensile diagonal bar equilibrates the force. Why am I neglecting the compressed diagonal? Yeah, yes. Well, this is an analogy made with the design of crosswind bracing steel structures. Generally, if you look around in most of the common cases when you have to build a fire escape staircase outside of the building, you use these trusses. Okay. And they are hyperstatic structures, because when you put a crosswind like this, it's statically redundant. But we designed them with a statically determinate scheme, neglecting all the compressed diagonals, because the compressed diagonal can buckle. Well, but here you will see, well, but that is a bar embedded into concrete. Yeah, but here we are designing for ultimate limit state. We can imagine that concrete is cracked and in some way can be even spalled out. So the effectiveness in confining the bar is lost. But that is the reason for which we have to provide the steel roofs, because we have to confine. But then you may also ask this. And okay, if I neglect and I don't find any equation where the compressed diagonal appear, how do I design it? Because if I don't have any force into it, I do not have any element to design it. So it remains, I can put there whatever I want. How do I design the compressed diagonal? The compressed diagonal is still a bar. So it means that I have to choose how many bars, which diameter I have to put there. Remember that the forces can come either way. So I designed the compressed diagonal exactly as equal to the tensile one, because when the wind or the earthquake comes from the other direction, what is tensile now becomes compressive. What is compressive now becomes tensile. So I have to provide resistance in both directions. Yeah, minimum is, it's just 2 wires in most cases. So this is very important. This is very important. This fact of neglecting the compressed diagonal is a simplification that we allow ourselves to have design equations which are simpler, more straightforward. Here you have an equation with just one unknown. But then we have to provide conditions to, fill the missing part of that assumption. But if this is a diagonal force, and it has a vertical component, it has also a horizontal component, as it's sketched there. Who is providing equilibrium to that horizontal component? You see, it's always a matter of being able to write equilibrium equations. When I explain this to my students, I do not want them to memorize this formula. No need to do that. If you are able to draw a diagram of forces and write equilibrium, this formula comes naturally. There is no need to memorize formula. Equilibrium, distribution of stresses, distribution of forces. These are the principles through which we have to work. Well, the equilibrium to this horizontal component will be provided by the forces into the struts. And the struts will be those portions of concrete whose height is 0.16 h, as we have more or less estimated. Well, actually, this is the case generic. But if our E is 0, as in the case, you see that these two forces are exactly equal. Then we have calculated the forces. We have calculated the forces in the tie and in the strut. So for concrete will be a matter of design. We know the grade of concrete. We know FCD. We know that this is 0.16 h. We have estimated it. And we know the width, 20 centimeters. So we know this. We can make the check. For steel, this equation can be used either way. It can be used for check, but can be used also for design. If you know the force, but don't know the area of the reinforcement, that equation there gives you the area of reinforcement that you have to put there. And see, these equations here also tell us another thing. The Q force, which is the force which has to pass through the coupling beams, as we have said, increases from the top to the bottom. So this also means that the amount of diagonal reinforcement that we have to put there, also will increase from top to bottom. So you may easily end out, and I guarantee you that from practical experience, you just need 5 or 6 story buildings. You easily end out with a reinforcement which can be so complicated that you hardly can allow it to fit in. Because you have seen the pictures. When we draw on a piece of paper or on CAD and so on, we may lose the feeling of the dimension. I remember once I designed a very simple truss, very simple, and it had to be the cover of a multi-purpose classroom in an elementary school. So I think it was 5 or 6 meter span. So not very high, very simple truss. But in order to accommodate the bolted joints, we did drawings in scale 1:1. So where at that time we didn't use CAD, we used paper sheet, and so we had drawing tables. Scale 1:1 because we need to know exactly the dimensions, the spacing, the distances, and so on. So that is the carpentry of steel. Detailing the reinforcement is exactly the same. Because you see, If you have, let's try to make a simple example. This is the cross section of your coupling beam, and it's 200 millimeter wide. Okay. Well, in a coupling beam, you can say I allow (20 millimeter of cover on each side. Well, especially if it's a residential building, this will be indoor. Well, it can also be outdoor. Okay, but you will have, additional plastering and so on. 20 millimeter is the minimum. You cannot go lower than that. So 20 millimeter cover means that actually the clear space that you have is 16 centimeter. And in 16 centimeter, you have, first of all, to accommodate, you have seen. If we go back to one of the pictures, you see here. You have anyway these bars here, and you have these bars here. So this is because you must provide a minimum, we call it technological reinforcement. It's a reinforcement that you do not bring into any kind of design equation, but simply because you never leave concrete with no reinforcement for more than a certain. So if you have to provide this, where we were here, it means that you will have here, for example, a bar like this and a bar like this. And those bars are 8, 10 millimeter diameter. I will not go lower. I will not go lower because nowadays, in most of the cases, 8 millimeter diameter is the lowest diameter in which you find steel with ductility requirements which are fit for seismic design. 6 millimeter bars, they are in we call A grade steel, which is not ductile as C grade. But what does it mean if this is 8 to 10 millimeter? It means that you lose 2 further centimeters. So the clear space in between here becomes 14 centimeters. And in these 14 centimeters, as you have seen, you have to accommodate some reinforcement here. But you have to accommodate these major diagonal bars. And well, if you are lucky, you just need 2 bars. But generally, those bars can be 20 millimeter bars. 16 in some cases if you are not very high demand, but generally 20 millimeter bars. In one of the cases, probably they were 40 millimeter bars, which go also into special provisions for bond, because what you find in the codes for bond covers bars up to 32 millimeters. More than that, you have to test the bond, because with such a large diameter, the forces which are transferred can become very high. But what if you use 20 millimeter bar? 20 plus 20 is 4 centimeters. So the clear space here is 10 centimeters, which is still okay. Which is still okay. If you have 4 bars, put them into this arrangement, but this requires more space. But it can happen because, as we said, this increases with the floor as you go down. So it can happen that you also need another bar in the middle. And what does that mean? Well, it means that from the original 14, you lose 6. The bar of those 14 occupies 6 centimeters. So the clear space between one bar and the other is just 4 centimeters. 4 centimeter is okay to guarantee the good flow of the concrete because we use aggregate 16 to 20 millimeters. And so the minimum spacing is the maximum aggregate size plus 5 millimeters. But there is a but. If you have to cast in place, then you assume that you are going to vibrate with poke vibrator. Poke vibrator, the minimum size is 7 centimeters, at least in Italy. So the vibrator does not pass through. Or which are the solutions? Well, vibrate at formwork or use self-compacting concrete, which does not require vibration. Actually, self-compacting concrete was developed exactly, among the other things, to solve the vibration issues in very congested areas. And the first structure in which it was used are the anchoring blocks of a cable-stayed bridge in Japan, the Akashi Strait Bridge, which is about 2 kilometers long. You can imagine it's cable-stayed bridge. You have to anchor the cables. You need heavy reinforcement because you have to accommodate the stresses due to the distribution. You know, these are all implications which come. This is a very simple structural element. Is the crossing of the bars, because then you have to take into account that if this diagonal goes from here, there will be this other bar that at a certain point will overlap. So actually this third bar, yeah, thank you. That third bar and even the fourth may be the diagonals coming from the other side. So you see, it's very, and having, you know, 2 bars for a diagonal, it's really the basic. You will not put one because one where you put in the middle and so on. So which are the solutions? Well, the solution can also be that we can, you know, employ a dual scheme of reinforcement. This dual scheme of reinforcement hypothesizes that there are longitudinal ties and a diagonal strut. Because you see, this longitudinal reinforcement, you have any way to put something of it. So why not using it? Well, you see here the equations are exactly the same. Simply, the longitudinal forces are now in steel and the diagonal forces now in concrete. So the equations are the same because these are equilibrium forces written for the same force Q and simply the force change sign. But the formula are exactly the same. But then you can say, okay, but which mechanism will occur? Well, you can hypothesize that they occur both and that they share the resistance. And how much do they share? Well, you can identify the one which is more critical from the detailing point of view. And the diagonal one is the more critical one because we must guarantee that the reinforcement crosses. So when you have reached your maximum capacity with this, it means that you cannot put any more reinforcement, any more diagonal reinforcement. Keep from that floor downward the diagonal reinforcement constant. This also means that the resistance of this mechanism will remain constant from that point down. Assign the additional counterpart to these other mechanisms, which will be a little easier to be designed because these are longitudinal bars. You generally put them in the, you know, bottom layer and so on. Well, equations, as I showed, are very simple. They are basically equilibrium equations. But then there is the ingenuity of the design capacity of the engineer to devise how can I make this mechanism to resist. This method is very simple because you can really, work it out on a piece of paper, but becomes, a little unpractical because it's based only on equilibrium. Becomes a little unpractical when you go for higher and higher rise buildings. So you need a methodology which can fit better. Well, in the slides, you find two methodologies. The Albiget-Goulet, it's a methodology based on continuum assumption. You have the development there. Let's focus here also because our time for the first part of the morning is ended. The frame analogy. So what do you do? Well, basically, you pick up your shear wall and you identify vertical wall piers and the coupling beams. Vertical wall piers are blue and the coupling beams are red. And you model it as a frame. But you see, these node regions here, since they are D regions, we model them as infinitely stiff. Then you solve this as a frame. But this is how much is 1, 2, 3, 4 stories. Can you tell me how many unknowns with the deformation method you will need to solve this frame? One rotation here, one rotation here, one rotation here, one rotation here. So one rotation in each node times 2 because you have 2 shafts. So 1, 2, 3, 4, 8 plus 1, 2, 3, 4 displacement. So it's 12 for a 4-story. And also, this is not a very simple, beam, because it's not that if you apply a rotation here, well, this goes down like this, and this has to do something like this. Because this is fixed and this is infinitely rigid. So actually, also, the coefficients, because when you have a beam like this and you apply a rotation phi here, you say that you have a moment for EJ over L here and 2 EJ over L here. But this is not exactly the case. So you need also to work out your stiffness coefficient. Or you have to put rotations here, 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 deflections there, so which overcomplicates the thing. So for this reason, when we go, and the issue is also that when you go for high-rise buildings, the deformation of the wall, all these assumptions are made on the assumption that the deformation is what we call one of the first modes. So it goes, like the classical deformation of a cantilever. When you go for very high-rise buildings, but this is an issue of dynamics of structures, you really might not have that. So for this reason, I will go quickly over this, but just to show you the methodology. There is this method, which is analytical one, in which what we do, we replace the discrete system of coupling beams. We have one coupling beam per interstory. We replace with a continuous medium. It's like if you pick up the coupling beam and smear it. So you have like infinite lamella. Okay, and we have, you know, some very strong assumptions. For sure, you must have a very regular coupling, a very regular wall with its geometry. So, first assumption, each element of the structure is linear elastic, homogeneous, and isotropic. And the properties are constant everywhere. Second assumption. All these elements are Euler-Bernoulli beams. Well, but we have just said the coupling beam is intrinsically not an Euler-Bernoulli beam. But what we have done here, we have taken the coupling beam and we have smeared. So you can imagine that the coupling beam is now transformed into a series of very thin lamella. So in that case, the lamella can be considered as an Euler-Bernoulli beam. Interstory heights are uniform. All openings have the same sides. Well, but you know, if you design a building, keep this, please. Cross-sectional properties do not change. Well, these may be not exactly true if you go for very high-rise buildings, because you may start with the width of your wall, and then as you go down, start with 20 centimeters, not less, but if you go down in a 200-meter high building, you can go to 30 or even. The cross-sectional properties of the coupling beams are all the same, except for the topmost one, which is half of that, because you smear that on half the story depth and not on the wall story depth. Coupling beams are axially infinitely stiff, but this is not a difficult assumption to make. We always make this assumption. We always make the assumption that beams and column are infinitely stiff. Floor diagrams are always there. Yeah, are helping, yeah, because to deform that, you also have to, you know, deform in some way the floor diagram. Then, shear deformations in the walls and wall shafts are neglected. We have seen yesterday that this is not exactly true, especially if you have squat walls or squat buildings. But if you go over high-rise buildings, this is okay. And the stiffness of the two walls, of the two shafts of the wall, is much higher than that of the coupling beam, and it's reasonably symmetric, so that we consider the coupling beams as fixed at both edges. Then we can use a very simple mathematical formula for the external loads, generally linear. So you see, we have a series of 11 assumptions. I have listed them there. So the method is based on a series of assumptions, which is very strong, but still, most of these are easily to beat. Then what you do, you divide the area of the coupling beam by the interstory drift and the inertia of the coupling beam by the interstory drift. This is already something strange because you cannot keep them both. But still we hypothesize, because here HEB is B times a depth. This is B times a depth to the cube. So we are dividing by the same quantity. So it means that either one of the other, then if you will try to match them, will not be true. And then what you do, so basically, you cut the wall at the middle. You cut the wall at the middle, and you say the coupling beams are transmitting the shear force. This small q is the q force that we have seen before, divided by the interstory drift. So you transform that series of discrete forces into a continuous flow. And they also guarantee the compatibility. Because since they are axially infinitely stiff, they guarantee that two shafts of the wall, they move together. If you work out the assumptions, I will not go into the mathematics, you will end up, because you find it and you are able to follow, you will end up with an equation which is like this. And what is that force T? That force T, you see this force T actually, if you start from the top, the force T is the integral of the shear forces in the coupling beam. So this equation here, you solve, and you find that T is hyperbolic sinus and cosinus. If you want to know Q, just calculate the derivative, because if T is the integral of Q, Q is the derivative of T. And then there is always the boundary conditions, which depends on this, and you find some examples there. But what is the power of this method? You can easily implement this into a script. I will not say XL5, because I don't know if you have seen on the newspapers yesterday, in Italy, there is this tall building, and there was a, insignia on the top, which was supported by a truss. Well, a part of that collapsed. Luckily, there was no, so everything remained on the top, but it was not safe and so on. And if you go on the social media and so on, you started saying, oh yeah, that is because the structure was designed by Excel and things like that, and the bolts. So still, but Excel is a very simple tool and so on, but sometimes it's useful. Our own script as structural engineers, we use software, structural analysis software. A software is for analysis, is not for design. Design is, there are softwares which give you already the reinforcement layout, okay. But the software is for analysis, but it's not for design. Design is a process which must involve your creativity, your thinking. And most of all, never forget one thing. In all the codes, it's written, because it may not be, that as a structural engineer, you must check the reliability of the results of the software. Because it's all your responsibility. If something happens, you cannot say, well, this was the result of the software. And how do you check the reliability of the results of the software? Well, you say, okay, let me see, the software gave me this kind of forces in this coupling beam. But if I pick up one coupling beam by chance and I use this hand method, what numbers would I get? Are they completely different, or do they in one way or the other match? This method here, for which you have all the, in the slides, you have all the steps, so you can easily write down in what kind of language you use, Python now. Young people use Python. Write down your own script in Python. Okay. And you will use a software, no problem. But then check it and say, well, let me see if this works. So let me run my Python script 30 minutes and see what does it. One more thing. We never think, or probably we overlook the fact that when we use a software for structural analysis, the software, what does require in input? Sectional properties. So you must already know the geometry of your structure, and that is already half of the design. The other half is the reinforcement, and sectional properties also require the reinforcement. So, and how do you assign them to the software? Just by chance, randomly, or you make a choice in such a way you are reasonably sure that your properties will be more or less. You use some very simple pre-designed equations. For a column, you easily can have the axial load on that. Divide that axial load by the design strength of concrete. You find the minimum area of concrete size that you need. And if you have the cross section of the concrete, you know also what the minimum reinforcement will be. So you already have an idea of your concrete properties. For the beam, once you have the width of the column, either if it's cast in place or precast, try to keep the width of the beam the same of the column. If it's cast in place, will guarantee easy formwork. If it's precast, will guarantee uniform distribution of stresses. What about the depth? Well, start, if you are cast in place, 1/10 of the span. If it's precast, we already seen, for example, with a pre-stressed element, which can be the typical ranges. So these are numbers. These are the slenderness ratios are numbers that you have to start, working with. And these do not require any special, tool, any software. Just do it. Then if you do this, then your software will provide you the answer, but you already know, oh, why that column is overstressed. Probably because I gave it a minimum area which was very, very close to the minimum one. So probably I can enlarge that a little bit. Why that beam is overstressed? Well, probably I can put a little bit more reinforcement there. So this will help you also to control these red points with red colors, which will come out of the software. So the software analysis is really the very last check. Also because inputting a model, it's time consuming. So you will not run analysis inputting models that you have go to change and so on. Also because, believe me, we always do that. We start very, very clean script, and then when we make modifications, the script, becomes more and more. And if more people work on it, it's difficult also to trace it back. So having tools to control the output of a software is fundamental. And these tools are always the basic models: equilibrium and constitutive relationships of materials. This is always what you have to get. Compatibility is something that we gave for granted in our. Okay? Well, let's have our coffee and snacks now, because it's, yes. Yeah. Yes, yes. In undergraduate level, we always have hand calculations. In graduate levels, for example, in the earthquake design class, we have some softwares for which we have the classroom license, and we allowed students to use them. But we still require that they extract a simple model. And the other thing, there is one thing that, if you use a software in the class, there may be the misinterpretation by a software house that the university has endorsed that software. So this is a wrong message that we do not want to pass. Imagine that we do have let's call it a column like this. Okay, typical scheme of a precast column, cantilever column. Okay, and let's call L, it's 8. Okay. On the top of the column, there is a load, an axial load applied, P. Okay. Well, this, for example, can be if you have a precast building like this. These are your columns, for example. which go into the precast foundation. And here you have your beam, which is like the beam that we saw that. So this is the way in which you model it. So if you have the self-weight here, Q, here you have QL half and QL half, and this will be your load P. So this is an example. So that very simple scheme is also something that you can easily find in the buildings. If you just go outside here, there is a elevated reservoir, an elevated tank for water. You design exactly according to this scheme. That is a cantilever shaft, and there is a big mass on the top. Okay? Well, this column under axial force, what kind of deformation do you expect? Do not run with your imagination. A column under axial force shortens. Okay? So you expect that this column shortens of a quantity which is P times L divided by EA. And A is the area of the cross section of the column. So if this is B and this is H, A is equal to B times H. Okay? Now, let us imagine that we do have the same column, exactly the same. That same load P is not vertical now, but it's lateral. So you can imagine in your building that here there is a facade, and the facade panel is in some way connected. For example, it's connected to here, to the beam, but there is a connection which transfers. So you transfer at this level here part of the wind force. What is the deformation that you expect in this case? Huh? Yeah, it's a cantilever, so the cantilever will deflect in this way. And you have this delta here. And how much is this? P L cube divided by 3 EJ. So this is delta axial, this is delta flexural. Let's try to calculate the ratio delta axial, delta flexural over delta axial. So it's P L cube divided by 3 EJ times EA divided by PL. So P and P simplify, E and E, they simplify. This is like this. A is equal to BH, the moment of inertia is BH12. So I continue writing here, this is BH divided by 3 BH cube, then we have an L square, and we have a 12 here. So this is 4 L square over H square. We have a column. We have a column which is subjected to a force. This force can either be axial or can be lateral. Actually, the lateral deformation, if we accept the fact that generally in beams, the column is 10 times the cross-section depth, more or less. Well, the flexural deformation, the lateral deformation, is a few hundred times larger than the axial deformation. This brings us to make two considerations. First thing, when we say that beams and columns are infinitely stiff axially, it's because of this. It's because the axial deformation, it's not that they are truly infinitely stiff, but their stiffness is 100 times higher than the flexural one. So in this case, you can, assume it much, much larger and so infinitely stiff. But there is another thing. There is another thing. The sensitivity of our structural elements to lateral deformation is much higher than to axial deformation. So now let us imagine that same column there is subjected not only to an axial force, but also to a lateral force, H. Well, it can happen that at the same time you have the self-weight at the wind. But there can also be some imperfection. Well, first of all, if you have the support, you might have friction there, but also some imperfection. So you can always have the fact that the beam, whatever small h is, you can always have that the beam already starts with a lateral deformation. And this load here, well, it moves with the top edge of the column. You see, generally, we neglect this fact. Because, as I have stated, we work under a very strong assumption of the structural mechanics that deformations are small and negligible. Small means that, okay, they are, small compared to the size of beam. We have said this morning, 1/1000th of 8 is very small, but even 100 is very small. But negligible means that you do not need to consider that the column or the beam are deformed. You can consider them straight and go ahead with your equilibrium equation. But what if deformations are no longer negligible? Well, if the deformations are no longer negligible, you see, it means that if you want to write your moment equilibrium here at the bottom, you will have that M is equal to P times L, to H times L. Plus P delta. So your moment, as what we say, consists of two contributions. This one is the first order moment. The first order moment you have writing the equilibrium in the undeformed configuration. You always have that moment. This one here is the second order moment. Second order because, well, there is an analytical reason, but it appears only if you no longer neglect the deformations. If you neglect the deformation, that moment does not exist, because neglecting the deformation, what does it mean? It means assuming that delta is 0. And if delta is 0, that contribution disappears. But you see, in precast structures, we have said that one of the advantages is that because of the better strength and better quality control of concrete, and because we cast horizontally, so there is better quality control of elements, we can have more slender cross sections. But more slender cross section means that that delta is higher. So it can be that it cannot be any longer neglected. And so it can be that instead of performing a first order analysis of your structure, you have to perform a second order analysis. Now, how do we do that? There is a little math, but it's very, very simple, as you will see. So let's draw back our column. This is P, this is H, this is L, and this column has a cross section here, BH, so that it has a certain Young modulus at a certain inertia. And we assume that this is constant, okay? So all throughout the columns has the same cross section. Now we assume that this column deforms in this way. And the force P and the force H, they, move with the tip of the column, with the top edge of the column, but they do not change their direction. The force P remains vertical because it's a gravity load. This same model you use for the wing of an airplane. And P can due to turbulences. In that case, P follows the axis of the beam. In that case, P will do like this. Now, the issue is this. If you look back into what we have written at the previous slide, I said there is a first order moment, HL, and the second order moment, and delta, you can say, is H L cubed divided by 3J. But then what is the effect? What is the effect? Is that you apply H, okay, and there is the displacement, and then there is P. And this P gets a moment. So this moment amplifies the displacement and increases. The displacement increases and the moment increases, so it amplifies the displacement. So this is likely a self-fed phenomenon. So we are interested in understanding whether this phenomenon stops at a certain point because the structure is able to find its equilibrium deformed configuration, or if this self-amplification at a certain point becomes so high that the structure falls down and undergoes what is called buckling failure. In order to do this, we have to, do a little mathematics. And the fundamental equation that we use you might remember that we have this equation in structural mechanics. The curvature, which we, mathematically describe as the second derivative of the deflection, is equal to minus the bending moment divided by the stiffness. But as a matter of fact, this equation here, without any meaning of y and x, does not mean anything. So first of all, we have to define which is our reference system in this case. Well, generally, x is the axial coordinate along the beam axis, in this case, the column axis, and y represents a deflection. Well, in this case, the reference system that we choose is a choice by the analyst. The analyst is the structural designer. So we can choose the reference system that we want. And actually, depending on the reference system, this equation may change its shape. In this case, we choose a reference system. I draw you here in orange. This reference system is centered on the top of the column, but in the deformed configuration. So it follows the top edge of the column, which is moving. X-axis describes the axial coordinate. The y-axis, with reference to a straight line, the y-axis is giving you how the beam is curved. In this reference system, how do you write mx? Well, in order to write mx, you have to imagine that at a certain point x, you make a cut. And this is your mx. And how much is this? Well, we have said there is a first order contribution and the second order one. The first order contribution is h times x, because we are here. And the second order is p times y of x. Well, why did I choose this reference system? There are two reasons. One is purely operational, because it's easier. But you cannot say I choose this because it's easier. Well, it's a reason. The other thing is that, as we have said before, we know how to calculate the displacement due to h, but then there is p, and p, has an effect on that. So we do not know actually that displacement, how much it will be. So if we choose any other reference system, we will be forced with an undetermined question, a question to which we do not have an answer. How much is in total that deflection there as the sum of the effect of h and p delta? So since we are not able to provide an answer to that, we just, put this reference system. So if I pick up this relationship here and I substitute into here, what do I get? I get the second derivative of x equal to minus hx divided by j minus pyx divided by ej. Or if I use a little of wisdom, the second derivative of y of x plus p over ej yx equal to minus hx divided by ej. This equation here is actually a linear differential equation, but it's very simple. It's one for which we know the solution. If we call this ratio here alpha squared, we get the second derivative of x plus alpha squared first derivative by x minus hx divided by h. So you see here we have an equation in which our deformation is unknown. Do we know the solution of this equation? Well, actually, we know from our calculus classes that the solution of this equation has a so-called general part and a particular part. General part is the solution of the same equation if you put 0 on the right-hand side, and this a sinus of alpha x plus b cosinus of alpha x. And the particular solution actually depends on what you have at the right-hand side. In this case, the particular solution, I don't go into the details, but it's minus h over alpha square ejx. The particular solution is a solution that if you put into the equation by itself, verifies that as an identity, and this is one. There you have some very simple rules of polynomial identity to determine that. So this is our solution, and depends on two boundary conditions. A and B. So in order to calculate A and B, we have to write the boundary conditions. And which are the boundary conditions in this case? In x equal, just at the bottom, which means x equal to L, what is that? Where repeat, please, louder. Yeah, the boundaries are x equal to 0 and x equal to L. Okay, but what shall we require? What shall we impose in x equal to 0 or and x equal to L? Displacement is 0 where? In x equal to L, you say displacement is equal to 0, and the second boundary condition? The slope, the rotation is 0. Well, I will say that of these two, one is correct, the other is wrong. Because actually, we have to write the boundary conditions in the reference system. The reference system is a reference system which is moving with the top edge of the column. So in that reference system, the displacement at the top is always 0, because I am moving with the top edge of the column. So I always see fixed at the top edge. What I see moving is the bottom edge. So the boundary condition has to be written in the reference system. Then it's true that the rotation at the bottom is 0. So it's a really important choice. So the boundary conditions in this case are in x equal to 0, y is 0, and in x equal to L, the rotation, so the first derivative of y is 0. It's true that the bottom is clamped, but it's also true that I have chosen a moving reference system. So it's like a problem of relative mechanics. It's like when you are traveling on two trains, your train is stopped and another one is moving, but when the other one starts moving, it's like you feel that you yourself are going far away from the other. It's a problem of relative mechanics. If you go on the website, there was a couple of days ago on was a photographer who made a very interesting exercise. He put a camera and he set the focus on the Milky Way. And he made this movie, and you actually see that the Milky Way is fixed and you see that the Earth is rotating. That is the same. If we would not have adopted this, we would have seen the Milky Way moving in the sky. So what this? If we put x equal to 0, the sinus of 0 is 0. The cosinus of 0 is 1, so we have b. Here we put x equal to 0, everything goes to 0, we have b equal to 0. Then we have to write the second boundary condition. So we first of all have to write the derivative, which will be a alpha cosinus of alpha x minus h over alpha square ej. I always consider that b is equal to 0, so I don't write anymore the term with b. So the first derivative in L will be h alpha cosinus of alpha L minus h alpha square ej equal to 0, which means a equal to capital H divided by alpha cube ej cosinus of alpha. And I write here the solution, which is y of x is equal to h alpha cube ej cosinus of alpha L sinus of alpha x minus h x alpha square ej. Is that correct? I'm just remembering that. Now, if I want to calculate the displacement at the top, what should I calculate here? Well, I should calculate y in L, because it's this one which will be the actual displacement. And this will be, you see, h alpha cube ej sinus of alpha L divided by cosinus of alpha L minus h L over alpha square ej. Which I can also write as h alpha cube ej sinus of alpha L divided by cosinus alpha L minus alpha. Well, it's a little bit hard to compare this formula with what we said before, that was h L cube over 3j. Am I right? But look, if I multiply and divide by L cube, nothing changes, correct? If I multiply and divide by 3, nothing changes. So I can write this as h L cube over 3j alpha, sorry, it's not. Is 3 over alpha cube L cube sinus of alpha L cosinus of alpha L. So actually what has come out it has come out that the displacement we can express as the first order part multiplied by this. This is an amplification factor. You can mathematically demonstrate, you can plot, but you know, that is the outcome. That the displacement is what we calculate or we know from handbooks, tables, and so on, times an amplification factor. What does this amplification factor depend on? It depends on L, and it depends on alpha. Alpha is the square root of P over Ej, so it depends on the amount of the load. There is one important consideration that we have to make. You see here I have at the denominator the cosinus of alpha L. Cosinus of alpha L can be 0 for alpha L equal to pi over 2. But alpha L equal to pi over 2 means alpha square, which is P over Ej, equal to pi square over 4L square. So when P is equal to pi square Ej over 4L square, cosinus goes to 0. It means that the displacement goes to infinite. That is what defines the buckling failure condition. This is called the buckling load. Well, in the reality, you know that no material, no structure will undergo and will be able to cope with an infinite displacement. The other thing is that what you will observe. So imagine that you have these forces here. You have applied H. H stays fixed. And P increases. We have said the effect of P is to amplify the displacement. So as long as you increase P, your displacement will increase. But as long as you approach to this value, the amplification will become larger and larger and larger. And at a certain point, you will go into a situation where the structure is not able to find its own equilibrium configuration and will collapse. So just, okay, this is a formula that probably you know is the critical load, buckling load of a cantilever column. But what are the implications? The implications in the design of a structure. Well, the implications in the design of a structure are this. Is that besides the classical strength model, you also have a buckling failure mode. So if you have, let us imagine that we do have a 400 by 400 millimeter column, 5 meter high, so L is equal to 5 meters. And we have a let's say 60 concrete. C60 means FCK equal to 60 Newton per square millimeters. Means FCD equal to 0.85 times 60 Newton per square millimeters divided by 1.5. 60 divided by 1.5 is 40. 40 times 0.85 is 34 Newton per square millimeter. C60 also means that EC is equal, what was that? 22,000 FCK plus 8, so was 60 plus 8 divided by 10, 2.3. How much is that? Should be close to 40,000. Eh? What? 39? Let's say 40,000. It's easier because it's more or less 40,000 Newton per square meter. Okay. So this column here, do you agree with this number? Well, 68 divided by 10 is 6.8. And 0.3 is close to the cubic root. The cubic root of 8 is 2, so I expect that the cubic root of 6.8 is what? 1.7, 1.8, something like that. 22 times 1.8 is close to 40,000. It's not that. So for this column, I have two maximum load capacities. One is the, strength. NRD is equal to AC FCD. And how much is this? It's 400 by 400 square millimeters times 34 Newton per square millimeter. Can you tell me how much is that? 5,000? 5,440 watt kilonewton. So it means a little bit more than 500 tons, just to understand. The other one is the buckling load. So we can say it's always an NRD because it's always a resistant buckling. And we can say it's, what is this? Pi square over 4 EJ over L square. So it will be pi square over 4 times 40,000 Newton per square millimeter times what is J is 400 millimeter to the fourth divided by 12 divided by L square, which is 25. This is E. This is E. This is J. B H cube, but B and H are equal, so it's like that. And this is 1 over L square. How much is that? 8,000? 8,422 kilonewton. So you see the buckling load in this case is 40, it's about 60% higher, more or less. There is a ratio 1.6. So, but it's more than half of that, or more or less close to 50% higher. But what if I use the same column over a 6 meter? Because you see, if the load does not change on the top, if you always have the same load on the top, you can say, okay, I keep the same column, I just give it rise. So how much will it decrease the buckling load? Well, you will have a 36 on the bottom instead of a 25. So, your ratio will be 25 over 36, which is close to 3 over 4, more or less. So your buckling load will decrease. whereas the gravity load will not change at all. But there is another thing. Let's put the numbers to appreciate that. Let us imagine that, you know, our precast manufacturer is so smart, and the structural engineer and the architect are so visionary that they want to go into a C120 concrete. Well, if everything applies, C120 FCD, instead of being 34, will be 68. And, oops, sorry. The maximum load capacity will simply double, so will be 10,000 880 kilonewtons. Okay? But what will be of the buckling load? What will be of E? Well, E will be 22,120 plus 8 divided by 10, 2.3. Accept that this formula is still valid. It can be, it cannot be, but don't matter now. Yeah, it's generally a fixed parameter. Yeah, you can use it because it's narrower, but we keep plus 8. This is from the codes. Okay. So how much is the Young modulus now? Huh? Let's say simply 48,000 is just for a matter of. So your strength has doubled, twice as much. Your Young modulus has increased by 20%. So what does it mean? Well, it means that your buckling load, the only thing which changes is the Young modulus. So your buckling load will increase by 20%. And if you make these things 8,422 plus 20%, you have to sum up something like 1660. So will be probably something like 10,000. So this means that we have reached the limit. The buckling load here is lower, not much lower, so they are more or less there to the bearing load capacity. These numbers, these examples, I wanted to put the numbers here because this clearly demonstrates you one thing. It's true that if we go with a higher strength of concrete, we can reduce the size of the elements. This is a benefit because we use lower concrete. Higher strength concrete costs more. So if we want to make it more effective, we need to use less volume of material. And since the ratio of reinforcement that we put in the column is proportional to the area of the concrete, it's good that if we reduce the size of the concrete, we will also proportionally reduce the steel. But the reduction that we can allow is not absolutely proportional to the increase in the strength. The reduction has to be proportional at a certain point to the increase that we get in the stiffness. Because if we reduce the cross section by half, which means reducing the sides by the square root of 2. So it's not that if you reduce the sides by 2, your cross section reduced to 1/4. And it's not. If you go from 40 to 260, 270, your load bearing capacity will be the same. But your buckling load will not be the same, will be reduced. So your cross-section reduction cannot be dictated by the proportion of increasing strength, but it has to be dictated by the proportion of increase in stiffness. Because if you go for slender columns, the buckling mode, slender columns and higher strength concrete, the buckling mode can prevail over the bearing failure mode. Well, now you have said, okay, but I made my, this estimate, this calculation here is very simple. You can do before you make any finite element model. You have an assessment of your loads. So you know what to do. You realize that for the building that you have originally intended, which is this one, cantilever column, simply supported beam at the top, your column will not be enough because its buckling load, in this case, its buckling load is exceeded. What can you do? You don't want to change your concrete because, for example, there is a special program you applied for some funding, and the goal of that funding was that you had to use 120 megapascal concrete. So you are stick to that. You cannot change the size of your building because this is dictated by the fact that you have to host some kind of activities there. You don't want to do, because if you increase the cross section, the cost of higher strength concrete will become higher, and so you don't want to do that. Is already, so you want to keep it like that. And how can we do that? By playing with the effective length. And what does the effective length depends on? It depends only on the end conditions. Okay? So you start from here. This is your building. And so end conditions. And what can you do for end conditions? Making the pin connection at the top as fixed. Okay, that can be, but that comes, with a complication, because a fixed connection, believe in me, most of the cases requires a wet joint, especially at that level. You don't want to do that. The connection at the top must be pinned. Then by bracing. And the easiest way of bracing is doing something like this. Okay? But then the cost estimate comes, and this additional cost of the bracing, because it costs the bracing, it's okay. These are, in this case, they are simply two steel ropes. They can be two steel ropes or two very simple L steel profiles. Okay, but you have to provide some steel carpentry plates to anchor them at the column. So these extra costs, there is no way to take it out from the budget. You have a fixed allocation. Huh? What is restoring action? Well, that means doing other things. So you cannot do anything else. Your budget is, you already, went out of the budget. Change? But you cannot increase, because since we said that that is the limit for which the C120 concrete can work. If you go higher, it becomes much more expensive. So you have added the bracing, so you have added some extra cost, you have to take out something. Reduce the height you cannot do because you have machinery moving there. That is one. So we have drawn here. Where was that? Here we have this very, huge fixed, the foundation element. So we can say, okay, I am satisfied, even if this is a hinge cross section, which will be easier and less expensive. And still the element is fixed, all the structure is fixed because we have the bracing. Okay. So in this case, if we want to single out the column from there, our scheme will be something like this. But now there is a but. Under that axial force, what do you expect from that column to do? Just shorten, isn't that? Nobody has a ruler, even a metallic ruler. Nobody has. Yeah, exactly that. Yeah. Why is that possible? No. Show that. Stand up and show. Yeah. That you can imagine is a pin column. Is compressing it. What does that column is doing? Is swaying sideways. Well, now the mathematical theory exists also for this case and was due to Euler. He was a visionary mathematician. So he said, well, I know that perfectly straight column under a perfectly centered axial force will only shorten. But at the same time, I hypothesize, I don't care whether it's realistic or not, I hypothesize that still there is this. And here I can put my X and Y like this. We will see the equation in a moment. There is buckling failure also in this case. But the buckling failure in this case is called latent buckling. Latent comes from a Greek word, which is lantano, which means I hide. So that buckling is hidden. What does it mean that it's hidden? It means that you don't see it up to the moment, to the very moment where the applied load becomes equal to the buckling load. So it's something which occurs suddenly. In mathematics, you say it's catastrophic failure because you have something which does not exist, is zero up to that moment, and from that moment onward becomes infinite. It's a hidden type of buckling. In reality, this never occurs. Why? Because actually we will never have, first of all, we will never have a perfectly straight column. It can have some, but also it's very difficult to have a perfectly centered axial force. In the reality, This is our column. Forget the constraint. There is a beam here on the top, okay? If this connection is hinged, what does it mean? It means that the beam is allowed free rotation. It means that the beam will do something like this. Well, it's difficult that it goes up and completely detaches from the beam, from the column cross-section, because there is a. But this means that you do not have a distribution of pressures transmitted by the beam to the column like this. You will likely have something like this. Because when it rotates, it will tend to push a little bit more downward and to relieve a little bit backward. So actually, at the top of your cross section, you will have your load applied with a certain eccentricity, which can depend on the tolerances, but can also depend on the adjustment, on the deformation that the beam, you know, if that has to be a hinged connection, the beam must be allowed to do that. And if it's allowed to do that, it will do, because of thermodynamics. If you have water and you open the tap, the water will flow out because of thermodynamics, because of minimum energy principle. So if the beam is allowed to rotate, it will rotate. But the effect of the rotation is that the contact pressures will be no longer uniform, but will have a linear distribution, which means that the position of the resultant force will be a little bit shifted. So this means, well, this is equivalent to a bending moment like this, equal to P times E. So this means that you will have now I draw, for the sake of simplicity, I draw it horizontally. This means that you will have a force P here, and you can have a bending moment M like this here. So if I put my x-axis here and my y-axis here, and this will be the deformation of my beam. And I have to write my equation here. What this equation will become. So let's, you know, here I have a force which is M over L, and here I have a force which is M over L. These are the reaction forces, and this is P. So if I want to calculate my moment, this will be minus M over L times X plus P y X. No, plus, because I start from here. Yeah. My bending moment, if I put myself here, is like this. Okay? Well, then it's exactly as before. Then it's exactly as before. I replace this into here, and I still have, if you work it out, an equation. You see this equation, if you look at its face, it's exactly as before. It's exactly the same as before. Well, there we had H, and here you have M over L, but it's exactly the same as before. So you can expect that its solution is once more A sinus of alpha x plus B cosinus of alpha x. And here you have minus M over alpha square L EJ over x. What has changed? What does change are the boundary conditions. Which are the boundary conditions now? We have x equal to 0 here and x equal to L here. In both, y is 0. In both, y is 0. Well, if I put x equal to 0, the sinus of 0 is 0, the cosinus of 0 is 1, so I have b, this is 0, this is equal to 0. And then I have a sinus of alpha L minus m over alpha square ej equal to 0, which means a equal to m over alpha square ej sinus of alpha L. Which also means that I can write m over alpha square ej sinus of alpha x divided by sinus of alpha L. I think it's minus x over L. And I do like that. Yes. Very, very easy. So the first thing that I see here, what has changed? Just because we had a different boundary condition, we had one different boundary condition. The first one is the same. Y in 0 equal to 0 is exactly the same. What has changed is here that in the other edge of the beam, before it was restrained, rotationally restrained. So y prime equal to 0. Now it's simply supported. Y equal to 0. What has changed is that here before I had the cosinus of alpha L. Now I have the sinus. What is the problem? Mathematically speaking, what defines the boundary condition? The buckling failure. Huh? The buckling, from the mathematical point of view, is a situation in which you have a structural element, beam or column, whatever it is. This structural element has finite dimensions, length, a cross section. It's real, so it has to be finite. There is a finite load, there is P. There is a moment which we have seen comes from P times an eccentricity. So the geometry of the beam is real, finite, and the loads are finite. What happens is that your deformation becomes infinite. But what is the effect? If y becomes infinite, also its first derivative becomes infinite. And the first derivative is the rotation. Also, its second derivative becomes infinite because the derivative is governed by the sinus of alpha x divided by sinus of alpha L. Sinus of alpha x changes, sinus, cosinus, minus cosinus, sinus. It changes periodically. But the sinus of alpha L always stays there. So it's not only the function y, the deformation, which goes to infinite, is the first derivative, the rotation, is the second derivative, which is the bending moment, is the third derivative, which is the shear force. So everything goes to infinite. So you have a paradox. You have a beam of finite dimensions under finite loads, and there is a value of the axial force for which this beam undergoes infinite deformations and infinite state of stress. This is the mechanical paradox. And when does this happen? Well, this happens when sinus of alpha L is equal to 0, which means alpha L equal to pi. You don't want, we know that it's alpha L equal to 0, but we don't want alpha L equal to 0. Because alpha L equal to 0 means P equal to 0, no worry. So this means P over Ej equal to pi square over R square, P equal to pi square over Ej L square. You have seen what has happened? Increased by 4 times because the effective length has increased by 2, and since it goes. So this is the importance of, once more, not only designing the connection, choosing the appropriate connections. What we have done here, we have first of all put a bracing. Bracing means, from the structural point of view, bracing means this, that in order to control the lateral deformation, we do not rely on the flexural stiffness of the column. In the previous case, we only relied on the flexural stiffness of the column. Now we are relying on the axial stiffness of the cross braces. Axial stiffness is much higher than flexural stiffness. Due to that, we could make a simplification also at the bottom. Now we will make a very simple example, and then I assign you an exercise for this afternoon. Very simple. So the exercise that I assign to you is to solve the same problem, but when the axial force is tensile. It takes 15 minutes, not more, so I will not disrupt your afternoon. Now, I know that you have also other classes this afternoon, so I don't want to be too much, but it's a nice exercise, but we will use it. But now let's try to do this. Let's try to solve this problem here. And now the challenge is this. I don't want you to write any more and to solve any more differential equation at all. So you have to solve this problem only with all we have already calculated. I just give you, well, let's make a small hint. The hint is this. We have solved this problem here, am I right? And we have found that for this, it's y of x equal to m over alpha square ej sinus of alpha x divided by sinus alpha L minus x over L. Okay? I have heard a whisper from this part of the class. Somebody said symmetry. Yes and no. Well, it's true that in structural mechanics, when we are under linear elasticity, and here we are making the assumption of linear elastic behavior, we use the principle of superposition of effects. But here, in analyzing the second order effects of the axial forces, we can use the principle of superposition of effect, but with a small care. It's true that we can say this problem is equal to this one plus this one. Yeah, but now the load becomes 2p, you will say no, because you have to apply the principle of superposition of effects under the same axial force. Otherwise, in one of the cases, you will lose the second order effects. So actually, you have not to go into the mistake of summing this up. So this means that you superimpose the effects of the flexural loads for the same axial force. So that axial force is like a characteristic of the structure. You don't consider anymore as an external load. It's like an ID, a DNA of the structure. Our structure is the structure under the axial force. Because otherwise, for this, you will have this solution. But if you take this out, this moment will not be affected by the force. And you want the same weight of the axial force. So if for this solution we add a reference system XY here, if in this case we put a reference system CY here, actually our solution will be exactly the same. Simply replace X with Xi. But what is Xi? Is L minus X. So then this is M divided by alpha square Ej sinus alpha L minus X divided by sinus alpha L minus X by L. Very simple. No more differential equation, just a little bit of wisdom. And then the solution will be the sum of these two. If you work them out, I have to change page, but sorry, if you work it out, it will be M divided by alpha square Ej sinus alpha X divided by sinus alpha L plus sinus alpha L minus X divided by sinus alpha L minus 1. Because you have minus X over L minus L minus X over L, and they will change. What do we do with that? Well, we can calculate rotations, deflections, blah, 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 whatever it is. What are really we interested in when we make a structural analysis? What do you want to calculate? Member forces. So for example, in this case, bending moment. And how do you calculate the bending moment? Well, bending moment is minus Ej, the second derivative of X. This is always true. So let's calculate the second derivative of this. How much is that? We have M over alpha square Ej. What is the second derivative of this first term? Is minus alpha square sinus of alpha X divided by sinus of alpha L. And what is the second derivative of this? It's minus alpha square the sinus of alpha L minus X divided by sinus of alpha L. Minus 1 with the already with the first derivative disappears. So if you have to multiply by minus Ej, you see the minus changes this into here, the Ej disappears, and also the alpha disappears. So your Mx is M divided by sinus of alpha L, sinus alpha L plus sinus L minus X. Interesting thing, because, you know, let's try to remember where we do have started from. We have started from this situation here. If you neglect for a moment the effect of the axial force, what is the diagram of the bending moment on this beam? It's constant. It's something like this. What is the diagram of the bending moment for that one? Well, it's an exercise that you can draw the formula, or you can open your computer, any MathCAD and so on, and you draw. But the question that we might and we must ask ourselves is this. This new diagram of the bending moment, does it imply the fact that there is somewhere a local maximum which is higher than m? Because this has a strong implication in design. Because if we start from neglecting the effect of the axial force, we will say the bending moment is uniform, constant everywhere, m, and I design for m. Then if I have to include the effects of the axial force, I end up with this. So I will say, okay, but this equation here, this function here, I don't care how will it effectively go. What I care is if in the 0 to L span, which is my domain of interest, I am not interested in minus infinite to infinite. I'm interested in 0 to L. In this domain, does exist a local maximum or minimum point? And in that local extreme point, how big is the moment? Is it higher or lower than m? How can I make this search? I am looking for a local maximum or minimum point of that function. I have to calculate the derivative. What is the derivative of this function, which on the other hand is the shear? Let me write it back. Mx is equal to m sinus of alpha L. Yes, sinus alpha x plus sinus alpha L minus x. What is the derivative of the bending moment? Is m over sinus of alpha L, alpha cosinus alpha L minus alpha cosinus alpha L minus x. Correct? You agree with me? Well, this is the derivative. I am looking for a local maximum or minimum. What shall I do with the derivative? Equal it to 0. When this is possible? Well, alpha cannot be 0. This is possible when cosinus of alpha L is equal to cosinus alpha L minus x. And when this happens, when the cosinus of two different angles is equal. Well, surely when they are equal or equal plus the period, but we are not interested in it. So this is true when x is equal to L minus x, which means L equal to L alpha. So actually, a local maximum point does exist at midspan because of the symmetry. And how much is the moment at midspan? Well, pick up L alpha and replace into here. It will be m divided by sinus alpha L. This is equal to sinus alpha L alpha plus sinus alpha L alpha, so it's 2. Still don't like this expression, too complicated to understand what's happening. Do you agree with me that I can write sinus of alpha L in this way? If I replace this here, this comes equal to m divided by cosinus alpha L alpha. What does this mean? What does this mean? This means that first, a local maximum for the bending moment in the 0 to L domain exists, is exactly at mid-span. And there, the moment is equal to m, which is the applied moment, divided by the cosinus of something. The cosinus is always lower or equal than 1. So it means that that moment is always higher than the applied moment. So the axial force, the compressive axial force, the effect is to amplify the moment, which is exactly what he was showing with the example of the copyboard. You apply a higher force, you amplify the moment, it means that you amplify the deflection. So if you want to draw, this is a parametric function, actually, depends on alpha. If we go back to our diagram of bending moment, it means that our diagram of bending moment will do something like this for increasing alpha, always at mid-span. So designing, neglecting these second-order effects of the axial force, in this case, cannot be safe. Because if you neglect them, you will design for a bending moment which is always slower than the true one. Because the axial force has an amplifying effect. And look at it. When the cosinus of alpha L alpha goes to 0, when alpha L divided by 2 is equal to pi over 2, so when alpha L is equal to pi, the buckling condition has remained the same. No matter if you calculate it on the y or on the moment or on shear force, the buckling condition is always the same because it depends only on the boundary conditions. Actually, we have analyzed two structures. One was the simply supported with one moment. The other one is simply supported with two moments. They are two different structures. The structure is the same, but the loading conditions are different. The buckling load has not changed. The buckling load does not depend on the external forces, on the external actions. The buckling load only depends on the boundary conditions. So it's not that if your structure is more loaded than another one, its buckling load will change. The buckling load is always the same. And it only depends on the boundary conditions. But one major outcome is that if we have a compressive axial force, the compressive axial force will amplify the effects of the other actions. Amplify in the worsening sense, because if you have a higher bending moment, it means that you are engaging more your structural element. The exercise that I have assigned to you complete it where it was. Complete it also with the other case in which you also put this. We have seen that it's very simple. And try to come out with how, in that case, the diagram of the bending moment goes. And tomorrow morning, in the first part of the class, we will dedicate that to understand the differences and what has happened. Okay?